We've talked about this idea of discontinuity. We've even looked at discontinuity, right? On here, you can see, and on the board I wrote down some other types, or some just the same types. There's 3 types of discontinuity. 3 types. One is a hole, one is a vertical asymptote, and one is what we call a jump discontinuity. Okay? Now they have other names. They have other names. The removable is the hole. So if you have a hole, they're not going to say a hole. They're going to say removable discontinuity. Okay, so those go together. We've talked about pretty extensively when there's a hole. Okay, so it's not a hole anymore. We call it removable discontinuity. Okay, and we talked about when it happens. When does a hole happen? What happens to the function? What creates a hole happening when we've had it? We've seen it. Why did it occur? Does anyone remember why it occurs? Yeah, Tristy?
It's an undefined value at that point.
It's undefined. What else creates it though? A little more specific. You're right. You're going along the right lines. Can anyone go any further? A hole. What happens specifically when we have a hole? Yes.
In that equation that it cancels out. Like
There you go. Yeah, cancels out. Something cancels out. Something factors out. Okay. So like we had something like this. We had something. You don't have to write this down, but we had something like this. X equals x squared minus. Oops. Yep. And then we had x plus 1, right? Well, this is difference of squares, right? So x plus 1, x minus 1, and then we have x plus 1 here. We had something cancel out, right? So another version of this is this here, x minus 1, okay? But when we have something cancel out, we have a hole. The 0 of whatever canceled out is the hole. So the 0 for x plus 1 would be -1. So we said we had a hole at -1, right? Okay. That's when a hole, that's what happens. That's when the hole happens. So at -1, at x equals -1, there would be a hole. Okay. That's called removable discontinuity. Okay. Asymptote, a vertical asymptote, right? A vertical asymptote is called non-removable, or sometimes it's called infinite. Sometimes I've seen it called both. Non-removable is most of what they use, but sometimes they also call it infinite discontinuity. Okay, so sometimes you'll see that wording too. Okay, that's when a vertical asymptote happens, right? We've talked about how to find those. We talked about why they exist, all of those things. The last one is what we call jump discontinuity. So they use non-removable, which is the same as this here, but you don't really see non-removable for jump. It's usually jump discontinuity. Okay. I shouldn't erase that, but there's 2 types of non-removable, a vertical asymptote or a jump, but most of the time they're not going to call a jump discontinuity non-removable. They'll just say jump discontinuity. Okay. So that occurs when at a value they don't meet. There's a jump. It looks like there's a big jump from the blue dot to the blank dot, right? That occurs when you have piecewise functions. When you have piecewise functions, that occurs. So most of the time, almost all the time you see one of these guys, it's going to be a piecewise function. There's going to be multiple pieces to it. Okay? Not all the time, but almost every time when you see this, it's with that. Okay? When you see this, there's a fraction, right? Numerator, denominator. Same thing with here, right? Same thing here because that's what causes the vertical asymptote. Okay? So let's say this. We got this here. Let's call this A. Call this A. call this A. Okay, so they're all at A, right? And where x is equal to A. Which of those have a limit that exists at A? So if I was going to ask you this, the limit as x approaches A for either of these guys, which would exist? The removable would exist for sure, right? Because you come from the right, you come from the left, it meets at the same spot, right? How about infinite? No, it wouldn't exist, right? One's going up, one's going down. What about this? What about if I have this? Let me draw this picture because I see this mistake a lot too. What if we have something like this? So we have vertical asymptote here, and then I have a function that goes like this, and I have a function that goes like that. And let's say this is at A again. What's the limit as x approaches A? Still does not exist. Yep, that's the right answer. Doesn't exist. Limit does not exist. The limit at A for this guy here is a DNE. Because I'll get some students saying, well, aren't they going to the same spot? They'll eventually meet, right? No, they won't. Because that vertical asymptote goes forever, right? This vertical asymptote goes forever. So as long as these guys are going down, that vertical asymptote's going to be there. So they'll never meet. They'll never meet. Okay? They'll never be able to cross the vertical asymptote to reach to the blues. This blue over here will never meet this blue over here, even though they're going to the same spot. They're going to negative infinity, right? So just be careful with that. Okay, so be careful with those. All right. Okay, so what is the definition of continuity then? If something is continuous. So continuity, I don't want to say, it's just the kind of the elementary, the low level definition of continuity is if I was drawing a graph, would I have to pick up my pencil? If I was drawing my graph, would I have to pick up, so if you were drawing this graph on your paper, would you have to pick up your pencil to draw this guy? So I could draw it like this. I can't keep going through though, right? I can't do that because it's a hole. So this guy I actually need to. I would go here, hole, and then go. So yeah, I would need to pick up my pencil. That's why it's discontinuous. This guy here, same thing, right? I could draw it like this, pick up my pencil, then draw the rest, right? Same thing here. I have to pick up my pencil. For something to be continuous, I wouldn't have to pick up my pencil. So something like a parabola, don't have to pick up your pencil. Linear, a cubic, something to the fourth power, right? You don't have to pick up your pencil there. But anytime you have to pick up your pencil, that's considered discontinuity, okay, if you were to graph it. Okay, again, that's kind of the elementary. It's not a correct definition. This is the correct definition. Okay, for something to be continuous, two things have to happen, or three things, depend on how you look at it. The limit at a specific x coordinate has to be the same as the answer there. The limit at a specific coordinate has to be the same as the answer at that x coordinate. Okay, so that's what this says here. The limit at some point, whatever x value this is, okay, the limit has to equal that y value. Okay, so this is the limit right here. This is the limit as not at 2, as x is approaching c, right? And this is the y value when x equals c. Okay, both of those guys have to equal each other. If they don't equal each other, it's not continuous. That's what we have to check. We're going to be doing a lot of checking today on, is something continuous at this point? we have to do this. We have to find the limit as x approaches that, and then we have to find the solution at that x coordinate. If they both equal each other, it's continuous. If they do not equal each other, it's discontinuous. And sometimes they'll ask you, okay, if it's discontinuous, if it's not continuous, which one will it be? We have to deal with that. Okay. In other words, sometimes you could do it like this too. The limit from the left side of a function is equal to the limit of the right side of a function is equal to, so it's another way of saying that, because this stuff right here makes up this stuff, right? For there to be a limit, it has to be equal. The limits on each side have to be equal to each other. Okay, so that's the definition. Either one is the definition. So on your first test, there's going to be an FRQ that says, is it continuous? And this is what I need to see. I need to see that I need to see that this equals this, or you can say that this is the same as this is the same as this, or one of them isn't true, and you're done. That is the definition, not words, right? There's no words here. This is the mathematical definition, or this is the mathematical definition. So that's how you show it. And that's how we're going to show it. I'm going to show you to you in your notes exactly how you would do it on an FRQ, okay? Because that's a big question to check continuity, okay? Okay, so let's try one with a graph. Let's do example number 1. This one's got a graph. Doesn't have a function like f of x equals, it's just a graph, okay? So what we have to do is find the points. When it says points, it means x values, not xy, x values. Find the x values, intervals, at which the function below is continuous, and the points at which it is discontinuous. Okay, so it's easier to find the points of discontinuity because they stand out. You know what they look like. They look like those guys, right? We're looking for those guys. Once we find those guys, then we can go back and say where it's those guys aren't. Okay, so first thing we got to do is find those guys. So let's write this down first. Discontinuity. Okay. Where are the points of discontinuity? X equals what? Or as x is approaching what? What's one point? X is 1? Yeah, x. When x equals 1, for sure, there's discontinuity there. Okay. Well, let's start with 1. Let's go with 1. Why is it discontinuous? What's going on there? What type of discontinuity? Removable. So we would say removable discontinuity. Okay, so now we're done with that one. What's the next one? X equals 4. X equals 4. Yep, I agree. At x equals 4, there's a discontinuity there. That's a jump discontinuity. Good. One more. X equals 2. Which one is that? What is that called? Non-removable. Non-removable discontinuity. Is there any more out there? Is any from 0 to 5? So only from 0 to 5. Is there any more? No, I don't think so. I think we got them all. Okay, good. All right. Okay, so now we have to put That's where it's discontinuous, right? That's where it's discontinuous. So now we have to put, where is it continuous? This is where there's discontinuity. So now where is it going to be continuous? X equals 3, I agree. At x equals 3, there's a point of discontinuity, or continuous, right? At x equals 3, how about at x equals 2.5? Is it continuous at x equals 2.5? How about at 3.5? How about at 0.5? How about at 1.5? How about at 1.25? How about at 1.75? You see what I'm doing here? There's an infinite number of things I could do that all day and all night, forever. So instead of doing that, how should we list them? Instead of individually, how should we list continuity? Not as individual points, but as intervals. Intervals from here to here. All right? It's like intervals. We have intervals, they're called periods. Period 1, right? Starts at 8:30, goes to 9:26. So it's like at 9:26 or at 9:30 or 8:31 are you in class? Yes. 8:32 are you in period 1? 8:33, 8:34, 8:30. We could do that all day, right? Or we could just say, listen, from 8:30 to 9:26 they're in period 1. That's an interval. We use intervals instead. Okay? So that's what we're going to do instead. Okay, so let's start with 0. Let's going to start with 0. Okay, so from 0, to where? From 0 to where does continuity stop? Not 0.99. Yeah, 0.999999999. We can keep doing that, right? So instead of writing that, let's write 1 with parentheses. What is the difference? So we haven't talked about that too much. Like, why don't I write it like this? What's the difference between the brackets and the parentheses for interval? It's called interval notation. What's the difference? There you go. Parentheses means everything in between 0 and 1. 0.00000000001 to 0.999999999. Brackets mean I want to include 0. Include 0, include 1. Well, I don't want to include 0 or 1 because I don't know what happens before 0. And I know for a fact at 1 there is removable discontinuity, or yeah, removable discontinuity. So that's why I put the parentheses. Okay? And then I use this little symbol here. It's called OR. It's a union symbol. That one could be, or what else? What else? Where are the continuity? Where else is the continuity? So let me color code this. So we got this part right here. We said this part is continuous. Where else is continuous? After 1 to what? To 2, right? Parentheses. 1, comma 2. Don't include 2, don't include 1, but everything in between. Good. And then we pick up at 2 and go to what? 4. Pick up 2, go to 4. And then after that, we pick up at 4 and go to 5 because that's where it said the interval ends. 4, comma 5. There you go. So when do we have breaks in our intervals? When do we have breaks at our intervals? Which coordinates or which x values do we have breaks in our intervals? At 1, because we have here, right? At 2, because we said it's discontinuity, and at 4 because we said discontinuity. Okay, so everything's covered. Literally everything from 0 to 5 is covered. There's nothing there that we didn't cover that we missed. It's either discontinuous or it's continuous. Okay. All right. Okay, so let's go to the next one. Okay. So they want you to use a graph. It's the same picture. It's the same exact picture, right? If you look on that one and then you look on the one we just did, it's the same picture from 0 to 5, and it looks exactly the same. They did that on purpose because now what they want you to do is only check at these places here. They only want you to check at certain locations when C is equal to any of those guys. Okay? But they want you to use the definition now. Oops. They want you to use the definition. So they want us to use this guy here, either the top one or the bottom one. Either this guy here or this guy here. So either 2 things are equal to each other or not equal to each other, or 3 things are equal to each other and not equal to each other. So I'll do the first one with you guys. It's not hard. It's just there's a certain way you have to write it that you might not be used to. Okay, so let's do C is equal to 1. So there's 3 things I'm going to set up for this one. The first one is I'm going to check at 1. So I'm going to plug in 1 for all of these C's. Okay, so I'm going to say the limit as x approaches 1 from the positive side equals, f of x equals the limit as x approaches 1 from the left side for f of x is equal to the overall limit for f of x, which is equal to f of 1. Okay, that's the definition. If all of those are equal, it's continuous. If one of them isn't equal, discontinuous. We know the answer. At 1, it's discontinuous. We know that. We just said that. But this one we're using the definition. This is what I want to see on your FRQs when you turn them in on test day, because that's the definition. Okay, so now what are we going to do with those guys? Well, I'm going to solve each of them. I'm going to solve each of these guys here using the graph. So the first one, the limit as x approaches 1 from the right side, the limit as x approaches 1 from the right side, what is that equal to? Go to your graph, what is that equal to? Positive 1, right? So you go, I'm approaching 1. Here, I stop here at 1, y equals 1. Okay, so that's going to be 1. How about the limit as x approaches 1 from the left side? What do I get when I do that? Same number, different number? Y equals 1. So if those 2 guys are equal, then what does the limit have to be? 1. That's the definition of a limit. If both of those guys are equal, that's the limit. You got your answer. Okay, so far so good. We got a bunch of 1s. Looking like it's going to be continuous. Let's look at the last one. What's f of 1 though? 3. And that's where it falls apart there. That's where it falls apart. Because that one does not equal, we have a hole. We have non-removable discontinuity. Okay? So what I want you to do is I want you to do that for 2 and 4. You know the answer. They're not going to be equal because we did that already. But I want you to set it up. I want you to write it this way so that on test day, when I ask you to use the definition or prove discontinuity or continuity, you know exactly what to do. Okay, so you're going to do the same thing, but you're going to do it for 2 and you're going to do it for 4. Okay. Okay, so the reason I'm having you do this is because this is the definition. I will get, this is what sometimes I get on tests. People will just write this. 1 equals 1 plus 1 equals 1 equals 1 does not equal 3. And my question is, well, what is 1? What is 1? What are the 1s and what are the 3s? I don't know what those are, right? You got to assume, you got to label everything. You don't have to do it in words. In math, we use a lot of symbols, right? F of 1, F of X. We use a lot of symbols for that. That's what you got to use. So this tells me, what am I trying to prove? And what do each of those values equal? Okay. So don't just write the numbers. You got to write everything because that tells you what you're trying to prove and if you proved it or not. Okay. So at 2. So at 2, from the right side, it looks like it's going to positive infinity. So this guy's going to be a positive infinity. Same thing from the left. From the left, it's going up to positive infinity. So if they're both going up to positive infinity, what's the limit? Overall limit. Does not exist. Does not exist. We just talked about that. We just talked about that right here, right? The limit at A right here won't exist, even if they're going in the same direction. It wasn't that picture, it was this picture here, right? This picture right here, right? Even if they're going in the same direction, they're never going to meet because the blue line continues, but so will that asymptote. So it does not exist. Does not exist. And f of 2 is undefined because there is an asymptote there. So these guys don't equal. These guys don't equal. So we would say limit, or we would say discontinuity at x equals 2. And then we know what kind, it's infinite, right? I don't have room to write this, but the last one for f of 4, so you would write the limit as x approaches 4 from the right of f of x equals the limit as x approaches 2, or sorry, 4 from the left of f of x equals the limit as x approaches 4 for f of x is equal to f of 4. Okay? And then you would say from the right, it's 1. From the left, it's 2. D and E here, because the limit overall at 4 doesn't exist. The answer, what's the answer? What's f of 4? Just f of 4. 1, yeah. That one doesn't equal either. Okay? All right, so we're going to have more practice with that right here. So most of the time, they won't give you a picture. And you can't use a calculator. These are non-calculator questions, so you can't graph it. So we're going to practice for the next 2 days at least. How do we do it? How do we do the same thing we just did up here without a graph? How do we do the same thing we just did? This question says the same exact thing. If not continuous, use the definition of continuity to explain. Okay? Well, you're going to have to use your thinking caps. You know where vertical asymptotes happen. You know where holes happen. You know where jump discontinuity happens, right? We just talked about that earlier. So look at A. What's going to happen at A? Tell me about discontinuity at A for A. Tell me where and tell me what kind that you know so far, that we've done so far this chapter. Yes, Tristy? There's going to be discontinuity at x equals 1. Yep. What, for what reason? Do you know? Because there's a asymptote there. There's a vertical asymptote, right? I can't factor it, so there's no hole. If I plug in 1 there, I'm going to get 0 on the bottom. I get 1 over 0. That means there's a vertical asymptote there. So we know there's a vertical asymptote. So I'm going to write a little note to myself. Vertical asymptote at x equals 1. Is that the only x value I could plug in that would give me a 0 on the bottom? Is there any other x value that I could plug in that would give me 0 on the bottom? No, that's it. So what they said is check this from negative infinity to positive infinity. Well, I don't have to do that. All I have to do is where I know there's going to be removable, or there's going to be some kind of discontinuity. And we know that there's a vertical asymptote at x equals 1. That's in the past, that's where we stopped. Now we have to show using the definition of continuity. Okay, so let's set this up. The limit as x approaches 1 from the right for f of x equals the limit as x approaches 1 from the left for f of x equals the overall limit, which equals f of 1. Okay. What is the, well, let's start with the ones we know. Which of those 4 do we know? Without having to, we know, we could find out all of them, but which of the 4 do we know is the answer? Which of those 4 guys do we know? We could figure that out. That one, the first 2 are going to take a little bit of work. Those 2 are going to take a little bit of work. How do we do this one? We know that, right? We know that. We already know that. We kind of talked about that already. If I plug in 1 here, I get 1 over 0. That means it's a vertical asymptote, right? So we already know that this guy's going to be what? D and E. We already know that, right? Which is the other one that I already know, kind of for the same reason that I just did. F of 1, right? What is f of 1 going to be? Undefined. Yeah. The other 2, the first 2, I got to kind of, it's either going to be positive infinity or negative infinity, right? The first 2, it's either going to be positive infinity or negative infinity. Same thing with the next one. Okay, I just have to figure it out. So I have to, in my head or on paper, I have to figure out as I get closer and closer to 1 from the right side, is it going to be a positive number or a negative number? Positive, right? If I plug in numbers from the right side of 1, 3, 2, 1.5, 1.4, 1.3, 1.2, 1.1, I subtract them, I get positive numbers, right? So this one here is going to be positive infinity. What about from the other side? Am I get positive numbers or negative numbers? So if I plug in 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.99, 0.999, am I getting positive numbers or negative numbers? Negative. 0.9 minus 1 is negative, right? I'm not going to get to 1, so it's going to be negative infinity. So we get a lot of things that don't equal. These don't equal. These don't equal. Those don't equal. We get a lot of things that don't equal. For all of those reasons, there's discontinuity. We would say non-removable. Discontinuity at x equals 1. Okay. All right. All right, let's do the next one. Let's do B, g of x. So before I start, what should I do first? Like the first one. The first one I saw, I'm like, we knew there was going to be vertical asymptotes there, right? So we investigated. We're like, okay, at 1, is there going to be any more? Okay, that was the pre-work, right? What pre-work should I do for B? There's a couple things I should do. What are the couple things I should do before I start actually doing the definition? There you go. Factor to make sure there's no holes first. And then once I factor, then maybe there will be a hole or even a vertical asymptote on the bottom. Okay, so let's factor first. Let's factor it first. Okay, so let's see. I'm going to factor the top. The bottom doesn't factor. It's just x plus 2. So let's see. Multiply to be negative 12. Add to be 1. That is 4 and 3. Negative 3. 2x squared minus 6. 4x minus 3x. 2x, x minus 3 plus 2. So it's going to be 2x minus 3 and x plus 2. That's what it's going to factor to. Okay. X plus 2 cancel out. So let's make a note of that. First thing, that's a hole at where? X equals negative 2. This is just informal. This is not our answer. I'm just writing this down for my benefit, so when I'm done, I can say this is where it's discontinuous. Okay? So the new equation, the factored equation, is just x minus 3. Is x minus 3 going to have any discontinuity anywhere? Is there any x values I could plug in for x that I would get undefined or anything? No. Doesn't have a bottom anymore. It's got 1 down there. So yeah. So the only thing I would have is an x minus 2. Okay, so all right. So now that I know that, I know there's no vertical asymptotes. I know there's just a hole at x minus 2. Okay, so now let's set up our definition. The limits for g of x as x approaches negative 2, because that's the only place that we saw there's going to be discontinuity. That's why I'm only checking negative 2 from the right. The limit as x approaches 2 from the left. The limit as x approaches negative 2 overall. And the limit, oh, not the limit, just g of negative 2. Okay, what's the limit? The easiest one to do is probably the limit as the overall limit. This is probably the easiest one to do. What is the limit as x approaches negative 2 going to be? Let's see. Negative 7, how'd you get negative 7? Plug in negative 2. We have, see, this is the place. We have a couple of different places. I could plug it in here, or I can plug it in here. 2x minus 3. That is what I'm going to use. Because, yeah, what happens if I plug it in over here? What happens if I plug in negative 2 over here to the original? I'm going to get something over 0, right? I'm going to get something over 0. That's undefined, right? So let's remember a hole. Remember what a hole looks like. So let me get another sheet of paper here. Remember what a hole looks like, right? So let me draw a picture. I have no idea what this function looks like because I can't use a calculator, so I have no idea what this function looks like. But I just know at negative 2, right? So negative 2, there's a hole. So this is not what the function looks like, but I'm going to kind of draw a picture. So kind of like that, and then negative 2, and then that, right? And then what else? What else is missing from that picture that it needs? Look at my picture down there and look at this picture. It needs a dot, right? It's not defined here. It's not defined there. We need to figure out where it's defined, right? So, okay, so if I plug in -2 here, we said that it's going to give me undefined, right? That's what's causing the hole there. So then, like Arthur said, when we plug in -2, we're going to plug it in here. What do we get as an answer? -7. So I probably should have moved this down. Let's see. Oh, no, I could have done that. -7. That's where the dot is. That's where the dot is. I have no idea if it's going to be positive, negative. I have no idea. I just drew a sketch just to kind of show you what a hole looks like, right? You guys kind of know it, but it's important to see it visually. Okay. So that is so at y equals -7, is that the limit or is that the answer? That's going to be -7 here, right? -7 is going to be here, not the limit. The limit's going to be somewhere else, right? Where is the limit going to be? The limit's going to be, see, that's where we do. We're not going to use this guy here for the limit. I only use this guy for the answer. I got to use this guy for the limit. So if I were to plug in numbers really close to -2, -3, -2.5, those kind of numbers, I would get something else, right? I would get something else here. So the limit, so that's the thing. Just be careful with that. When you have a hole, when do you use this guy and when do I use this guy? I only use this guy for my solution, g of -2. I use this guy for the limit because they're in two different spots, right? The only time this guy right here is going to give me something I don't like is at -2. Everywhere else, it's going to give me an answer. Everywhere else, it's going to give me an answer. That's why I need to use this guy here at -2 because this guy gives me an answer. Okay, so when x equals -2, use this guy. When x is anything else, use this guy here. Okay, because that's where it's going to be. So there are actual values here. This guy has a limit. This guy actually does have a limit. It's just we have to figure out where it's going to be. So how do I figure out where it's going to be? How do I figure out where the limit's going to be? At -2. Can't plug it in, right? I can't plug in -2 here. Because what happens when I plug in -2 there? I get undefined, right? Which is the reason that hole's there. And then if I plug it in -2 over here, great. But that's not going to be the limit, right? That's just the solution. So how do I figure out the rest? That's my question. How do I figure out where it's approaching? How do I figure out where it's approaching? I'm not going to tell you because you guys can do it. How do I figure out where it's approaching? So I have a saying in all my classes, but mainly this one: try me now or try me later. Try me now means try now when what's the penalty if you get it wrong? Nothing. You get it wrong, right? Try me later on the test. What's the penalty when you get something wrong on the test? You lose points, right? So do you want to try it now or do you want to try it later? So those of you looking at me waiting for me, if you want me to do this, I'll do this. But then guess what? There's going to be one just like this or even harder on the test. And I don't think you want to see it there. Okay? So try me now or try me later. It's up to you guys. Okay? It's up to you guys. You guys can do this. You guys know what I kind of showed you a picture. You know what a hole is. Find the value. Or just tell me a method for doing it and we can do it. Tell me a method for doing it.
Use numbers close to -2.
That's what I would do. I would use numbers that are close to -2. In my head, plug them in and see where you're at. And see if it's the same spot as the other side. So pick numbers that are close to -2. Plug them in. I'd probably plug them in over here because this one's easier to plug in. Or you can plug them in here. It's okay. If you pick numbers close to -2, pick the close -1, 0, -3, -4. What number are you getting close to? When you know, let me know. What is the number going to get close to? It involves pencil and paper. Once we're done with this, we get back up. Okay, so yeah. So if this one and this one and this one, if they're not equal to each other, well, we obviously know they're not going to be equal to -7, but that's what we would use. So we would say removable discontinuity at -2. Once you fill these in, you're done. Okay. All right. Okay, so we're going to finish tomorrow. We will finish these notes tomorrow. So you have a couple assignments still out there. One's due today, one's due tomorrow. Okay, so if you haven't finished those assignments on Delta